Thanks everybody for, in particular Julianne, for letting me switch spots. And yeah, so pretty much everybody here, or almost everybody here, has heard me talk about this FIRE project, the project for the last few years that we've been working on with the simulations. And I know James also yesterday talked about some of the work that we've been starting to look at with these new simulations, that it's basically, I've been trying to build up from these simulations of isolated disks into cosmological simulations with a more explicit treatment of the ISM and stellar feedback. So this talk is not going to be really telling a narrative. It's going to be the kind of talk I normally hate, which is just sort of a rapid fire list of different things that are happening, advertisements for work that's ongoing by collaborators with these simulations, with the hopes that those of you who are interested will get in touch with these people. Many of you already know them. But you might not know what they're working on right now. So just the brief overview I will give is, what are these simulations? What are we doing? Again, most of you are familiar. Well, we're trying to build up better intuition for galaxies by modeling the feedback in ISM more explicitly. So the simulation movie here isn't just because it's pretty, it's showing an example of one of the simulations of an isolated galaxy with parsec scale resolution and putting in as much as we can the physics we think should be there for the ISM. So you reach high resolution, you put in the appropriate cooling, you restrict star formation to the very highest densities so that stars are forming not just in GMCs, but in sort of dense subregions of those GMCs. When stars form, you take the feedback straight out of your favorite stellar evolution model like Starburst 99, and Oscar described this. And here we track all of these things explicitly and separately. So they all have their own time dependencies. They all follow the standard stellar evolution models for time dependence, mass, energy, momentum, metal injection, etc. And that includes supernovae 1A and 2, stellar winds from both young and old stars, photoionization, photoelectric heating, etc. And of course the momentum from all of these sources, which has been discussed already. And as Oscar pointed out, an important thing about the momentum is that all these things are actually comparable in momentum space. So there's really no good way to drop any of these terms. And that's been one of the more striking conclusions from these kinds of simulations, is that the nonlinear effect of all these different interacting feedback mechanisms is really more than the sum of the parts. And then more recently, we've also ventured into scary physics of MHD, conduction, diffusion, etc., and I won't have time to talk about any of that. Here's what happens when you embed all of that in a cosmological zoom-in run. So this is a Milky Way mass galaxy in formation. Some of you have seen this movie before. Here's a mock HST. Sorry, actually a mock UGR composite, not HST, but similar. And on the right is the gas in color coding, the cold, warm, and hot gas. And the box is a couple hundred physical kiloparsecs on a side. So it's big compared to the galaxy at very early times, but about the size of the virial radius at late times. And what you can really see, very strikingly, is this picture that has been around for a while, but has really become evident in the newest generations of simulations, where there's this very violent early phase where things are accreting rapidly, things are merging rapidly, things are unstable. As Avishai said, it's kind of pointless in these very early stages to try and slice it up into which exactly each of these mechanisms is contributing towards things being a train wreck, because it's basically the whole thing's a train wreck the whole time. And then it calms down at later times as accretion rates slow down. And what you see is these very violent outflows at early times that blew most of even the cool and cold material out of the galaxy in big bursts settle down. And that last one at z of 0.7 was triggered by a passage of a companion. But since that time, this particular simulation settles down and accretes a more extended intermolecular and outer ionized disk that actually starts to look something like a plausibly realistic disk. And then there's a very late merger that comes in right at the end of the simulation. But even that actually doesn't completely destroy the disk down to z of 0. It just has its first flyby here, and then just ruins the z of 0 image by falling back in right at the last second. But
it's got to happen to somebody.
Yeah, exactly. But nonetheless, you can, find a lot of galaxies that start looking, not orders of magnitude away from reality out of this. So All right, now on to some of the results and work in progress. So this is one of the results that's out there, but Chris Hayward is going to be picking up on this and looking at this in more detail. But I think one of the most striking results, which Oscar already mentioned, is that the Kennicutt-Schmidt relation, when you put in all of these feedback mechanisms, emerges naturally, and that's what's shown here. Every galaxy at every time plotted on the Kennicutt-Schmidt relation, and the yellow shaded range is just the 90% contour for the compilation of Genzel and Leroy's and Kennicutt's data. And this just falls out fairly naturally, this couple percent efficiency per dynamical time. And in particular, it falls out completely independent of what we set the star formation law in the simulations to be. So we can change the small-scale star formation law in the simulations, the rule for how the densest gas above 100 particles per cc turns into stars. We can make that conversion happen 100 times or even 1,000 times faster, or 100 times or 1,000 times slower, and we get the same global relation. Because what this is really telling you is not how fast is gas on large scales free falling down to become stars. If it was telling you that, all these points would be shifted up by a factor of 100. It's telling you how many stars or what rate of forming young stars is needed to stabilize this surface density of gas, to essentially maintain it marginally stable against runaway gravitational instabilities. And that seems to emerge very robustly, and other people are seeing that as well. Now, of course, we saw outflows in these simulations, and that's what many of the people here are very interested in. So Sasha Muratov, a postdoc at UCSD, has been looking at this, quantifying the outflows in the simulations very rigorously in terms of both observational metrics, but also theoretical metrics in terms of different phases and how rapidly they cross different radii away from the galaxy. This is one of the punchline numbers that many people are interested in, the mass loading of outflows, the outflow rate relative to the star formation rate, averaging over time, otherwise there'd be a lot more scatter for all different simulations. So each point here is a different simulation. And you can see there's a trend where low-mass galaxies have very large outflow rates and high-mass galaxies have low outflow rates, and all of this fits in with long-standing theoretical and observational ideas, and you can see the outflow rates get as high as hundreds of times the star formation rate in the smallest galaxies, although big galaxies, it's more like about equal. And in particular, if you like to turn things into very simple sort of power law scalings, we already heard about this distinction between an energy-like scaling and a momentum-like scaling. That just is shorthand for a power law that goes as VC to the -2, circular velocity to the -2 in the blue line, and in the black line, a power law that goes as VC to the -1. And you sort of see a transition. There's some curvature in this relation that Sasha's finding, where you could plausibly say, okay, the massive galaxies are more momentum conserving-ish, and the low-mass galaxies are more energy conserving-ish. And that does happen for a physical reason, namely that in the low-mass galaxies, the densities are much lower, so you can go through an energy-conserving sort of Sedov-Taylor type phase when overlapping supernovae explode for much longer and build up more energy. But it is important to note that by the time the outflows are any significant distance from the galaxy in these simulations, they're not energy conserving, they're momentum conserving. It's just that you built up more energy, more momentum in that earlier energy conserving phase inside the disk. And that's why you get this sort of broken scaling. But of course, it depends, as we know from observations, on where and how you measure it. Yeah. It seems to be, is it giving weird feedback? Okay.
No, it's better when it's on.
Okay, sorry. All right, I'll do that. Yeah.
Sorry.
No problem. Sorry, I'm being annoying about it. All right, so here's a plot from Sasha's work on the total mass that's been expelled in units of the stellar mass of the galaxy through different shells just for one of these simulations. And he's broken it into a couple of temperature bins as a function of the virial radius. And the point is, okay, most of the outflow mass near the galaxy is in the cool and cold phases, the less than 10 to the 5 Kelvin gas, just because that's what most of the gas in the system actually is composed of. That's this blue set of points here, whereas the hot gas is a smaller contribution for this particular simulation. But not surprisingly, the hot gas is what's actually able much more efficiently to get out to large radii. Most of those cold outflows don't make it very far. They make it maybe to tens of % of the virial radius, but then they fall back. They're fountaining back much more quickly. So when you talk about outflows, it really does matter where you're measuring them for what you should see and for what it's going to do to the galaxy. And of course, an incredibly important theoretical point that we all know, but I think we often ignore when we construct our subgrid models, is that there's no one-to-one relation, between star formation rate and outflow rate. There's a huge scatter between these two quantities. This is just for one galaxy over a narrow range of redshifts. There's a huge variability in both of these quantities, and there's lots of physics that gives rise to scatter between them. And so that can have important effects. As we heard earlier, right, bursty AGN feedback can be qualitatively different from continuous AGN feedback. The same is true of stellar feedback. So maybe a simple way to improve some of the subgrid models that we're using in large volume cosmological simulations is to account for this scatter the same way it was proposed earlier that we account for the stochasticity of AGN feedback. Now, of course, what are the consequences of these winds? The one result that's in the paper that's already out is the consequences for the stellar mass function. And that's shown here. So this is the stellar mass-halo mass relation. The dotted line is what you'd get if all the baryons turned into stars. The colored lines are Peter Baruzzi and Ben Moster's compilations. And these are the default runs where we just take parameters as is from Starburst 99. And I show this, as I've said before when I've given this talk, just to emphasize that, not to say that this is a solved problem, but to say that it's shocking to me that we're even in the right ballpark with this, simple approach. That it seems like we are maybe starting to converge on the most important physical mechanisms that regulate star formation. And that's enough to get us at least in the right order of magnitude ballpark. Although I'll come back to what's happening up here in a slide. But there's a lot more detailed metrics that we can look at and should look at and are looking at. So Freke van de Voort is now at Berkeley, has been looking at galaxy morphologies. This is one example of the morphology in gas and stars of a particularly disky simulation that came out. But the point of this particular example, this is the distribution of angular momentum showing it's extremely strongly peaked around circular orbits, and that's for the stars and all the stars. There's no light weighting even in that. The point is simply that it is possible to have strong feedback and thin rotationally supported systems at the same time, or in the same galaxy at least. Because there have been some claims that maybe the two are somehow mutually exclusive, that strong feedback always destroys disks, and maybe feedback can't be the answer. And that's not the case. And the reason is what we saw happening in this movie, that you can have this sort of strong transition where in the early stages, yes, the feedback is very violent, and you wouldn't see what you'd call a thin disk in those stages. But you can sort of have two equilibria, right? There's the quasi-spherical, everything's pulsating and getting thrown in and thrown out equilibrium. But then if you get calm enough and things get thin enough and you're stable enough, you can vent, right? Your outflows don't move through the entire disk and blast out your thin disk. They vent out of the plane of the disk in the poles, and you're able to maintain a decent outflow rate without actually destroying the disk. But if that's what's happening, and that certainly is what's happening in this particular simulation, that's a real challenge because actually resolving venting is really hard in simulations. We're barely doing it in these simulations with 100 million particles in this galaxy. It's a real challenge. And now a new student at Caltech, Janice Schmitz, has been working with Freke and has started working on more statistical analysis of the morphologies over a large population. Basically, very preliminary results that I'm showing here, but it is clear that the morphology is more sensitive than things like the stellar mass to the details of feedback as well as numerical details of how we implement things. So the integrated stellar mass of these two runs, exact same initial conditions, is essentially identical, but in one of them we turn on and turn off this multiple scattering of infrared photons approximation that those of you who've been at conferences where this came up know that there's been lots of debate about what really can happen in this regime. And there's very little difference in most of the galaxy properties. You can see outside of like 1 or 2 kpc, the rotation curves are essentially identical. The masses in stars are basically identical. But at the very center of the galaxy, this does make a difference because at high redshift, the stuff that formed this very center the galaxy was dense enough that it was marginally optically thick in the infrared, and thus some of these more complicated effects can be important. So I don't know which one is the right answer. I just want to say that it does matter, and we can hopefully start to break some degeneracies with these kinds of comparisons. It's also worth noting that, morphologies are a little bit chaotic. So you rerun the same simulation 10 times. Even if you don't change the physics, if you just change your random number seeds, you're going to get slightly different answers. But we can try and make some statistical statements. And that's part of the reason why we haven't rushed to put out the morphologies are this paper yet, because we really wanted to make sure we knew what the morphologies were in these simulations. And the challenge, of course, running zoom-ins is you never know what the morphology is supposed to be. You don't know that the universe wanted that halo to be an elliptical or a spiral. You just know what you got. But for example, this run that looked so disky, here's a bunch of different runs of it with essentially random nuisance parameters varied. And you can see there's a significant variation in the bulge to disk ratio. The blue line, the light blue line here, though, is what happens if we just turn off feedback, where then, okay, it's totally a bulge, which isn't super surprising. So we can at least conclude that there's a real difference systematically between those. Dushan Kiras has been undertaking a huge numerical study of the different numerical effects and their role in this. And this is showing a numerical study in the existing paper, but he's built on this quite extensively of the ratio of stellar mass to halo mass in simulations where we vary purely numerical parameters, things like resolution, treatment of artificial viscosity, how we soften gravity, etc. And of course, these differences can be significant, factor of 2 or 3, but I just show this to highlight that compared to the physics differences, they're very small. So for example, this one point here was run with old-fashioned bad SPH that can't do Kelvin-Helmholtz instabilities, Gadget 2 era SPH. And the point immediately next to it was run with our fanciest modern SPH that does a great job capturing fluid mixing instabilities, etc. And that's the difference in their stellar masses at Z of 0. Because it's a totally gravity and feedback dominated problem, this doesn't have as big an effect, which is good news for most of the people here in this room. Those of you who know Dushan know I was using an old picture of him in there. He's grown a very large beard in the last few years. But that said, there are areas where this makes a big difference. In particular, where we do find the numerics makes a big difference, confirming what many people have said before, and in particular, the Arepo group has emphasized, is that the cooling from the hot halo is sensitive to the numerics. So as you push to more massive galaxies, where the late time halos are hot and most of the inflow is in the regime where the cooling time is longer than the dynamical time, you do have to worry about numerical details, because things like the mixing of these small clumps of cold gas changes the cooling time significantly in the hot halo. So there you see a big difference between sort of Gadget 2 era and modern era simulations. And Gizmo is the name of our new code, which I'll describe at the very end of this talk. I'll give a very brief advertisement for. But there's also other areas where it's clear that explicit treatment of the feedback makes a difference compared to the simplest sort of subgrid model. So on the left and right, I'm showing the IgM temperature here in a 200 kiloparsec box. In the current simulations here of another Milky Way-ish mass galaxy, here using the sort of Oppenheimer and Debye feedback model, where we just, proportional to the star formation rate, throw gas out of the galaxy at a constant multiple of the escape velocity. You can see things are much gentler here, and this goes to the point I was making earlier about the sort of stochasticity, the multi-phase nature, the fact that there's not one velocity but a distribution of velocities of outflows leads to a very different structure of the IgM. And Claude Fauché-Giguère has been looking at comparisons that we hope can really constrain this with the distribution of gas around galaxies. So there's incredibly active, this is an incredibly active area observationally right now, people measuring gas around galaxies in the CGM. And so we're trying to hopefully use this to really constrain the dynamics of feedback, because different outflow material has different phase properties depending on how it's being blown out of galaxies. Now, of course, the most extreme example is shown here. No feedback, with feedback, same galaxy. Okay, this is the red and contoured regions are the things that would be, I think DLA is, I can't remember actually what the column density threshold that's plotted there is. But you can see the covering factor of absorption is massively enhanced by the winds in the right. That's not that surprising. And this is a comparison. The points versus the point with an error bar is Gwen Rudy's observations, and the points are some of the simulations. This is extremely preliminary, so what we can say right now is the no feedback models don't work, but we're trying to narrow down what does work. It seems to work over a range of covering factors, so this is showing the covering factor versus halo mass average inside the virial radius at high column densities, lower column densities, and the colored points of the simulations, they seem to work pretty well explaining a lot of the observations, except X had to go and find these quasars that have this crazy high covering fraction, and nothing we have in our simulations seems to approach them. So maybe that means there's missing physics in the simulations. Maybe it's physics unique to quasar-type systems like AGN outflows, which I would love, because that's something I've been arguing for a long time. But maybe these systems are just weird in some other way, and we don't understand that yet. But they're the big outlier right now. A grad student of mine, Shengcheng Ma, has been starting to look at the mass-metallicity relation. This is zooming in on a region of the mass-metallicity relation for very low-mass dwarfs. So the green points are observations. These colored points are the simulations here. I can show you the high mass end, but that's not as interesting. The simulations agree well with the observations, but so does almost any sane model that you put together. But down here, it's not actually trivial to agree. So if I take those old feedback models, this curve is basically what I predict as the track. And that's actually in the Oppenheimer and DeVay papers, as well as in the new Illustris simulations. That's what they found. They had to add a parameter, which was some mass-dependent metal loading factor to get this to agree well. And the problem is that to explain the mass function of these tiny dwarfs in a simple model where outflow is proportional to star formation rate, you need to blow out 99.9% of all the baryons that ever got into the galaxy. And it's very hard to do that without blowing out 99.9% of all the metals that ever got made in that galaxy. But these galaxies don't have 0.1% of the metals that were ever produced in them. They have like 10% of all the metals that were ever produced in them. So they've held on to more metals than gas, basically, which is telling us something cool about how feedback is working. Either it's suppressing new pristine material getting in, or it's being preferentially reaccreted if it's metal rich. We don't know yet, but it's work in progress. Freke van der Voort just had a paper looking at a completely different aspect of metallicities, namely whether or not our process, abundance patterns, could be explained by different scenarios for neutron star mergers in these simulations. The punchline is it seems plausible, but there's a huge uncertainty in these models, so if you're interested in this, in our process elements, I'd check out her paper. I'd also check out Xijing Shen's paper, which was on a very similar subject, approached it with different simulations and models, but came to, I think, similar conclusions. A grad student of Dushan's has also been looking at this question of cusps and cores. This is TK Chan at UCSD. And James already talked about this. I just will very briefly show what TK has been looking at is more the mass dependence of this cusp core scouring process. And that's what's shown here. Basically, this is the slope of the mass profile versus halo mass, and higher is more cored. All that's really happening here is the statement that around 10 to the 11 solar mass halos is kind of a sweet spot for getting the strongest cores, where at higher masses, too many baryons pile up in the center, and they pull the dark matter back in. And at lower masses, you just don't have enough energy from supernova feedback to slosh around the gas so much that you create that big a core. So this is completely work in progress. It's basically the first plot he's made on this, but it's exciting stuff. I'll skip this. We're looking at escape fractions as well with my student Shengcheng. The conclusion is our escape fractions at high Z are low. And the higher resolution we push, we run simulations down to Z of 5 with 20 solar mass particles. We're running them now with 5 solar mass particles and sampling the IMF and everything. And they just get lower the more we push the resolution. Because the problem is it takes time to clear out dense gas around young stars, and it takes about the same amount of time to evacuate the dense star-forming regions as for those stars to die. So unless you invoke something like runaway stars, it's very hard to get out of that. Paul Torrey at MIT now is starting to look at AGN in these simulations. Anything I would say about AGN would be incredibly premature, so I'm going to say a couple things about AGN. It seems like from the very limited initial analysis, we've been running nuclear scale simulations, putting all of these ISM physics, but also a bunch of more realistic AGN physics into the simulations, but not really following the AGN feedback over long time scales. What we can say right now is that the accretion rates actually don't look wildly different with explicit treatment of ISM physics versus the old, simpler subgrid models, namely because the accretion rates we found were always dominated by gravitational instabilities, and those still dominate the accretion, so that's hard to get around by just making the medium more turbulent, for example. But that accretion rate can have a big effect on your galaxies. So Daniel Anglès-Alcazar just started at Northwestern, and this is from work he did in the last year, but he's starting to look at this in our simulations. If you put in, for example, the old prescription for black hole accretion that was based on assuming the Bondi-Hoyle rate versus what we actually see whenever we simulate small scales around black holes, which is something dynamical that regulates accretion like gravitational instabilities, you get actually very different growth histories for the black holes, and you even end up with a different M-sigma relation. Here with no feedback, so maybe feedback completely just throws out this story and rewrites it. But the interesting thing he finds is that they get a Megorian relation that has the right slope with no feedback, just using this gravitational instability model for accretion onto the black holes. The black holes are 20 times too massive, so there still needs to be feedback in some sense. But maybe it's just that you throw the stuff out and it doesn't actually see the galaxy on its way out. All right, Eric's hovering over my shoulder, so I'll conclude quickly.
Please do.
All right. So the other punchline I'm going to say that I'm going to point at Robert Feldman, even though he hasn't actually started looking at this, but he made the mistake of volunteering to look at this, is the fact that we don't see any quenched galaxies in these simulations. And we've pushed it to higher and higher masses, still without seeing anything quenched. So this is a 10 to the 14 solar mass halo. These dotted lines are the observational constraints on what its stellar formation history should look like, and here's what we get. It just keeps rocketing up and has a huge cooling flow at the end of the day. Basically, there's no AGN feedback in these simulations, but what we can say, I think fairly robustly, is none of these mechanisms, none of the non-AGN mechanisms, all of which we've included in the simulations, including things like late-time heating from AGB star ejecta shocking against the gas, that's in these simulations and has been from the beginning. It doesn't work. It's not enough to stave off a catastrophic cooling flow problem. So other physics is needed. All right, this was my, our detailed argument on the AGB star aspect. So I'll conclude there. Those are a lot of the projects in progress, but there's a lot that's, as I said, preliminary, and you should stay tuned. There's a lot of new results that'll be coming out, and somebody asked me, and I'll give you a couple slides on the new code that we're going to be making public in a couple of weeks. So that was my, please ask me. All right, I'm good.
So you're going to come up and get connected. We have time for one or two questions.
Bill, could you comment on your efficiency of stuff animation, which you're taking 100% in any place when it comes to stuff animation, which, so kind of routine mechanics, what's the use for stuff, and your energy, it's about more than 10 times more than anybody else.
Mm-hmm. So the
We're going to unplug.
all right.
Sorry. I know it's pretty, but
That's okay, yeah. That's an advertisement for the new code called Gizmo. It'll be made public in a couple weeks. I'll be happy to talk to you offline about it. In response to your question, so in dense regions, we assume, what we do is we assume that in dense self-gravitating, locally self-gravitating regions, the efficiency of gas turning into stars is 100% per free fall time. Now, as I said, you can change that pretty dramatically, and it doesn't have much of an effect. But you just pile up more dense gas is what happens, right? If you need more young stars to self-regulate, that's where the bottleneck will be. So more and more gas will pile up at that density until you're turning enough of it into stars that you get the right stellar mass. Now, the motivation for using that high a number, 100%, was just so that we could be, honestly, part of it was just so that we could be clear that we were absolutely not putting in the 1% by hand, pedagogically. Sure, it's put in by hand. But there actually is a motivation for that I think is real. Now, the way you can test this observationally is by measuring the amount of that very dense gas in galaxies, things like the HCN-CO correlation, because that pileup will be visible then in the dense gas tracers. But the physical motivation is, if you look at the people simulating GMCs, when the clouds are bound, the formation efficiency relative to the global dynamical time is 100%. It's maybe 50%. It's not 0.1, it's not 0.01.
Okay, so let's quick question, quick answer from.
Quick answer. So I'm confused about what you're saying about the regulation of star formation rate. Off your last slide, I typed in star formation is feedback regulated. And I also hear you, I think, saying that star formation rate is governed by needing to balance the dynamical instability. That sounds like two different things to me. Do you?
Well, it's that you're balancing an equation. On the left-hand side is feedback, which is proportional to number of young stars, which is proportional to star formation rate. And on the right-hand side is rate at which I'm getting rid of momentum by gravitational instability, rate at which my disk is collapsing, essentially. And it's when those two balance that you get equilibrium. So what you get as the prediction is the Kennecoott-Schmidt law, because the surface density of gas times the orbital frequency of the disk gives you those terms from the right-hand side that tell you how fast the disk wants to collapse. The normalization of that relation comes from all the terms that are basically how much feedback do you get per unit stars you form. It's basically the average mass to light conversion efficiency of stellar populations gives you the normalization of the Kennecoott-Schmidt relation. And you can trivially see that by if I just double m over L or double L over m of my feedback model, I have my predicted Kennecoott-Schmidt relation because I need half as many stars to get the same feedback.
Okay, great. We'll have to ask questions later during the discussion. So thank you again.
Projection, et cetera, and that includes supernovae 1A and 2, stellar winds from both young and old stars, photoionization, photoelectric heating, et cetera, and of course the momentum from all of these sources, which has been discussed already. And as Oscar pointed out, an important thing about the momentum is that all these things are actually comparable in momentum space. So there's really no good way to drop any of these terms. And that's been one of the more striking conclusions from these kinds of simulations, is that the nonlinear effect of all these different interacting feedback mechanisms is really more than the sum of the parts. And then more recently, we've also ventured into scary physics of MHD, conduction, diffusion, et cetera, and with a more explicit treatment of the ISM and stellar feedback. So this talk is not going to be really telling a narrative. It's going to be the kind of talk I normally hate, which is just sort of a rapid-fire list of different things that are happening, advertisements for work that's ongoing by collaborators with these simulations, with the hopes that those of you who are interested will get in touch with these people. Many of you already know them, but you might not know what they're working on right now. So just the brief overview I will give is, what are these simulations? What are we doing? Again, most of you are familiar. Well, we're trying to build up better intuition for galaxies by modeling the feedback in ISM more explicitly. So the simulation movie here. Thanks everybody for, in particular Julianne, for letting me switch spots. And yeah, so pretty much everybody here, or almost everybody here, has heard me talk about this FIRE project, the project for the last few years that we've been working on with the simulations. And I know James also yesterday talked about some of the work that we've been starting to look at with these new simulations, that it's basically, I've been trying to build up from these simulations of isolated disks into cosmological simulations. It isn't just because it's pretty, it's showing an example of one of the simulations of an isolated galaxy with parsec scale resolution and putting in as much as we can the physics we think should be there for the ISM. So you reach high resolution, you put in the appropriate cooling, you restrict star formation to the very highest densities so that stars are forming not just in GMCs but in sort of dense subregions of those GMCs. When stars form, you take the feedback straight out of your favorite stellar evolution model like Starburst 99, and Oscar described this. And here we track all of these things explicitly and separately. So they all have their own time dependencies. They all follow the standard stellar evolution models for time dependence, mass, energy, momentum, metal, and we won't have time to talk about any of that. Here's what happens when you embed all of that in a cosmological zoom-in run. So this is a Milky Way mass galaxy in formation. Some of you have seen this movie before. Here's a mock HST. Sorry, actually a mock UGR composite, not HST, but similar. And on the right is the gas in color coding, the cold, warm, and hot gas. And the box is a couple hundred physical kiloparsecs on a side, so it's big compared to the galaxy at very early times, but about the size of the virial radius at late times. And what you can really see, very strikingly, is this picture that has been around for a while, but has really become evident in the newest generation